Hi everyone, welcome to part 2 of our memory lecture. I hope the first one made sense to everyone. And in this part we're going to be looking at free space management and how that is handled by the operating system. So what is handled in terms of free space management? Well, splitting, coalescing, keeping track of memory region sizes, as well as multiple strategies for maintaining and managing memory. So all 4 of these concepts and topics we're going to be looking into in this part, the first of which being splitting. So splitting is finding a free chunk of memory that can satisfy the request for memory allocation and splitting it into 2, right? The one being the one that is allocated and the other being the remaining free chunk. So the first example we're going to be looking at in terms of splitting is when we request memory that, or a block of memory that is smaller than a size of a free chunk, or smaller than the size of free chunks. So let's look at this example here. There are 2 10-byte free segments with a 1 byte request. So we're trying to find space for 1 byte of data. And in total we have this 30-byte heap. So we have 0 to 10 is free, 10 to 20 is allocated, and 20 to 30 is free. So what does the free list look for this if this was our entire memory, or our entire heap in this case? Well, the head here points to the first address, which is at a 0 of the first free chunk. And it also indicates, or this node in the list indicates the length of that chunk, which is 10. And then it points to the next free chunk, which is at 20. And that is also of length 10. So this is what it would look like before splitting. All right? And then after, obviously, we get our request. And now this is what it looks like after splitting. So here you can see we've allocated an additional 1 byte from this second free chunk. So now the free chunk, instead of starting at 20, starts at 21. And you can see our length, or the length of that chunk, has been reduced to 9. Now you might be asking, why did we pick this one over the first one? Well, for now, just think of that as random. But in later, when we talk about memory management techniques or behaviors, then that's where we'll look at different approaches to which one we pick. Okay, so that was splitting. Next, we're going to be looking at coalescing. So it's kind of like the opposite, right? Where we merge we merge a free chunk with existing chunks into a large single free chunk. So here we go, another example. So when we are requested memory that is bigger than a free chunk, the list will not find such a free chunk, right? It doesn't exist on in the free list. So when this happens, we require coalescing. We require the merging of multiple free chunks. So here we go. We have a 3 10-byte free segments represented by this free list. So you can see each of them is 10 bytes, and they're at different addresses. One's at 0, it starts at 0. Another one starts at 20, and another one starts at 40. And we receive a 20-byte request, so we need to find space for 20. So what would happen after coalescing? Well, you might assume that, okay, well, we have a single node now that starts at the first address of 0 with a length of 30, right? 10 plus 10 plus 10, that is equal to 30. Now, this is in fact wrong. And the reason for that is that these like free chunks or free nodes, they're not next to each other. There is data stored in between these. So if you were looking at your overall memory layout, it would basically be a free chunk, an allocated chunk, a free chunk, an allocated chunk, a free chunk. So coalescing actually doesn't work in this case because these nodes are separated by like stored data. So before coalescing you would have this, and after coalescing you would have exactly the same free list setup. And that's because coalescing only allows you to check like adjacent memory addresses to see if you have in fact got two free chunks or free nodes that are adjacent to each other. So what I'm going to do, I know I quickly cycled through the slides there, but on this slide here, you can see that I've changed the free list setup a bit here, where now we have address 0, length 10, address 10, length 10. So these are hypothetical nodes or this hypothetical list. Well, they're adjacent. So what ends up happening is coalescing can occur for either one of these nodes. And after coalescing, you can see what it looks like here. Again, we can't actually merge this last node because it's not adjacent. But now we have address 0 and length 20. So these two nodes here have collapsed into this last one. And then what could occur then is we could fulfill this like 20 byte request because this first one here has a length 20 now. So it would actually, that request would gobble up this entire node, and what our free list would look like after this request would be that the head simply points to this node here. So we've talked about coalescing and splitting. So how do we do this reorganization of our free memory in an efficient way? Well, this requires two components, or performing two things. The first is we need to be able to track the size of these allocated regions, okay? And we also need to be able to embed our free list directly onto the heap so that it is accessible. So the first component, tracking the size of allocated regions. Now, the reason why we know that the operating system is doing this for us is because of the free function, right? The free function does not take a size parameter. You just say free, and it happens all behind the scenes. So how does that library, that free function, know the size of the memory region that will be back into the free list? Well, the solution to this problem is found in how memory is allocated in the first place. Now, most allocators store extra information in a header block. So this header block stores like metadata regarding the data that has been allocated. So in C, you would say like pointer is equal to malloc 20. And then the header, or the actual allocated region, would look something like this here. There would be a header component used by the malloc library, as well as the actual 20 bytes of data allocated. And the pointer that you would have declared here points to the start of that region. So whenever you allocate memory and you utilize pointers, you're not actually pointing to the very, very beginning of that allocated region. You're pointing to the start of the data section of that allocated region, which is found directly after the header component. And it is this header component that keeps track of, say, the size of the block. It also keeps track of a few other things. So firstly, the header minimally contains the size of the allocated memory region, like we talked. So here, hypothetically, you would have size equal to 20. But the header may also contain additional pointers to speed up deallocation, as well as a magic number, which is utilized for integrity checking. Now, it's not really important to know the specifics of these things, but just know that there are other components or other information stored within this header section. And there's actually two pointers: a header pointer which points to the beginning of the header, and then the pointer component which points to the actual data, or the 20 bytes returned by the caller. Now, obviously, this has been defined as some sort of structure, and hypothetically, you could see on the right-hand side here what this structure would look like. So it would have a size variable and as well as a integer variable to store the magic number, and this would be our structure for our header. Okay. So that means that the size required for our free region is now the size of the header plus the size of the space allocated to the user. So if a user requests, say, n bytes, the library searches for a chunk of size n plus whatever the size of the header is. And we can use simple pointer arithmetic to find the header pointer. And you can see some code here that would basically demonstrate that. So a pointer to which points to the start of the header is basically equal to the pointer that's pointing to the data minus the size of the header itself. So if I go back here, if we have this pointer which is pointing to our data and we subtract the size of the size in which the header takes up, so this size here, obviously we would then get to the pointer or the head pointer. Okay, so moving on to the second part, which is embedding a free list. So our memory allocation library initializes the heap. Okay, and at this point the heap would be empty. And then what it does is it puts the first element of the free list in the free space of that heap, which is completely empty. But we have a little problem here. And that problem is that the library that is required by malloc to actually allocate memory can't use malloc itself. Okay, you can't call something to build itself in that sense. So I'll explain this a little bit better because I know it can sound a little confusing. But what this means is that we have to therefore embed the free list directly into the heap. So the free list has to exist within the heap for it to be utilized, and you can't allocate the free list using libraries that require the free list to exist, so we have to do it in a different way, and that is by embedding it directly inside the heap. So once again we have a little structure that represents what this free list looks like, and we talked about this in the first part, where we have some size. So this is a node within a free list, right? So it indicates the size and it has a pointer to another node. Just your classic linked list style structure. So now we've kind of expanded our picture out a little bit, where we have a header structure, which is used for representing allocated blocks. And we have a free list node structure, which basically is the description of a node of a free list. So we can use both of these components or these structures to represent different chunks of data, allocated and unallocated. So this is hypothetically what it would look like in memory, or sorry, in the heap. And here now you have a head pointer and a pointer for our allocated block, and you have a head pointer for the free block. Once again, the header for the allocated block is basically just the size and that magic number. And now the header, or the component within the free block, has a size as well as a pointer to the next free block. So it's currently pointing to 0 because there is no other free block. So this is, you can think of this as null, like a null pointer. Okay, so first things first, what happens during allocation? So if a chunk of memory is requested, the library will first find a chunk that is large enough to accommodate the request. And this is done by iterating through the free list and checking the size. Okay, so for that previous one, you basically start at the head, check, then move on to the first node. We see that, okay, it's not big enough, we'll move on to the next one, not big enough, move on to the next one, okay, it is big enough, and therefore we can place or allocate the memory from this chunk. So the library will split the large free chunk into two, and we're talking about this, the splitting operation. And one for the request, and other one being the remaining free chunk once again. And it will shrink the size of the free chunk in the list, so just to update that there's no longer this amount of free space. So I think an example will help just with explanation in terms of performing allocation. So in this example, we have a request for 100 bytes, and that was requested by using the code, like a pointer is equal to malloc 100. And now this is the process of what would happen, and I'll demonstrate with like a little graph or figure afterwards, but this is basically what's happening. So firstly, you're allocating 108 bytes in this case, and I got 108 because my header is hypothetically 8 bytes large. So that's 100 for the 100 here plus 8. And then I'm shrinking our free chunk that was hypothetically originally 4088 in terms of size, 4088. And then we subtract that 108, and that will give us 3980. So what does this actually look like? Well, here we have our heap, a 4 kilobyte heap with one free chunk, no allocated data, and the size is 4088 as I alluded to in the question, and it points to next, so it's not, there is no other chunks that it's pointing to, and this is what would be the representation of your heap before this allocation. And this is what it would look like after you have performed the allocation. So now we have an allocated block and we still have a free block, okay? And this allocated block is now one in which we've allocated 100 bytes to be utilized. And it's important to note that this size is not 108, right? It is the size of this allocated chunk here, not the entire block itself. We have our pointer, which points to the start of this data. And we have our remaining free block, which you can see now has been reduced in size. It still points to 0 because it's just a single free block and there's no additional free blocks. But now it is smaller by 108 bytes. Cool. So that's what happens during allocation. Now moving on to maybe a more in-depth or complicated example. Here we have a 4 kilobyte heap with 3 allocated chunks. So we've got one chunk here, we've got another one here, and our third one here. Okay. Now I'll speak about this S pointer in a little bit, but firstly you got to note that in this example we're going to be looking at freeing memory. So here's a chunk of 100 bytes that has been allocated, but it is about to be freed. Okay. Now in order to free something, we utilize the free method, or like a free library. And this library, this method specifically, takes in a pointer. And if you remember in the previous example, I alluded to it, but I have this pointer here which is pointing to some memory that I want to free. So that's how it works, right? We request to free memory at this particular pointer. Okay, so let's have a little bit of an example. Now here we see that there's a request to free a chunk of memory, and we want to free 100 bytes chunk back into the free list, or move it back into the free list. Now how it works is that this new free chunk is added to the front of the free list. Here we have what that process now looks like in terms of in the heap, right? So if you remember, this was those allocated bytes that we wanted to free, so now they are freed. Our head pointer of our free list now points to that newly freed section, or chunk specifically, sorry. You remember our S pointer was pointing to this region, and now this chunk points to the previous head of the list. So you're adding these chunks to the front of your linked list, not the back, which is maybe something you're more familiar with. So you add to the front, and this repeats every single time, right? You free a chunk. That chunk now becomes the first structure or chunk within the free list, and then it now points to the previous head. So you can see here our next variable is pointing to this chunk over here. So let's take this example a step further and say we free the remaining chunks. Okay, so one by one, each of these chunks will be freed and then added to the front of the free list. Now what you end up getting is something like this. So now our head pointer points to this chunk here, which is hypothetically the last chunk that was freed. This chunk, sorry, this arrow should be on the next, not on the size. This chunk points then to another node or another chunk that was freed second last, which then points to that chunk that we demonstrated in the previous example, which then points to the final chunk, which then points to 0 or nothing or null. So that's what your the process of freeing memory looks like on the heap. Now, there's a slight issue with this, is that you can obviously see fragmentation occurs, right? We've got these pointers going all over the place, not just nicely forward down to the list, as well as the fact that we've only got freed chunks, but we've got lots of separate freed chunks. So how do we manage this free space? Well, obviously in this case, coalescing is needed. Okay, but there are other techniques as well that are important. So if you remember back earlier, I said that you could have picked either the first free chunk or the third free chunk, and I just said think of it as random at that point. Well, now we're going to be looking at specific ways in which we manage this free space in terms of when do we pick what free chunk to utilize for which request of memory. So there's quite a few different strategies. Some of the basic strategies we're going to be looking at today. The first being best fit. So here, as the name says, you find free chunks that are bigger or bigger than the request, so like the same size or bigger than the request, and you return one of the smallest chunks in this group of candidates. So you're trying to find the chunk that is big enough to fulfill the request, but the smallest of those. So it's the closest matching chunk that is big enough. Then we have worst fit, and that says finding the largest of the free chunks and allocating the amount of the request. So you just look for the largest free chunk and you allocate to that chunk. And you keep the remaining chunk on the free list. So if you allocate 20 on a free chunk of 120, obviously you keep the remaining 100 on the free list. First fit, finding the first chunk that is big enough for the request. So as you are looping through or iterating through your free list, as soon as you find a chunk that is big enough to fulfill the demand, you place the memory in that location, as well as returning the requested amount as well as, sorry, to repeat myself, the remaining rest of that chunk. Next fit, so you find, it's the idea here of finding the first chunk that is big enough for the request, so kind of like first fit, but you don't restart looking at the beginning of the list. If your pointer is currently pointing to somewhere midway through your free list, then you just start off from where you left off, in other words. So it's the idea here of searching at where one was already looking instead of at the beginning of the list. Cool. So some examples. Say we had our free list that looks something like this, and we were given the request which required us to allocate size 15 memory, or 15 bytes. So in terms of best fit, this is the result you would get. So remember, best fit was you find the smallest free chunk that is greater than or equal to the request size. So here, this is size 10, so that's not big enough. This is size 30, so it is big enough. This is size 20, it is big enough, and it is smaller than the other candidates, which was this one, right? So that means that we allocate our memory in this chunk here, this third chunk. And what we can see is after performing that allocation, well, the free list has changed. So now our length is 5 because it used to be 20 and we allocated 15 of that 20. So 20 minus 15 is 5. And the address has also changed because now, where before it started at 60, well, now there's 15 bytes here that are allocated, sorry. So then this address is shifted 15 bytes to the right, or in the resultant free list. So that's why it's 75. So that was for best fit. Now the next example is worst fit. So worst fit, we just find the biggest chunk that fulfills the demand. So that would be this second one, which is of length 30. And we have a demand of 15, so 10, that's not big enough. 30 is big enough, 20 is big enough, and this is the biggest one, so that's why it's the second one. And now we see, well, after performing that allocation, the length is obviously needs to be reduced by 15, and we see that, so 30 minus 15 is 15. And now the address is also changed, just like it did before, from 20 to 35, because now there was those 15 bytes that have been allocated basically in front of this this address. So that's why the address shifted 35 to the right. Now this address obviously doesn't change because nothing happened to this chunk of memory, as well as the length didn't change. So that is the result of worst fit. Now there is another approach that is a little bit more technical, and it is called buddy allocation. So it's not a basic strategy, it's more of like an advanced strategy. And this is a binary buddy allocation algorithm or system. And here, the allocator divides free space by 2 until a block that is big enough to accommodate the request is found. So what does that look like, right? So say we had a chunk here of free, like a free chunk, okay? And we were given a 7 kilobyte request. So obviously this is way bigger than our request size. And for example, if this was worst fit, you would just put it in here, right? So what the buddy allocation does is it says, okay, let's divide this chunk up into 2 and continually divide it up until 2 until we have a chunk that is big enough for the allocation size. So we divide 64 by 2. That gives us 32. Still way too big. Okay. We then divide 32 by 2, and that gives us 16. Still too big. We divide 16 by 2, we get 8. Now the question is, why do we stop at 8? Well, if I divided 8 again by 2, we would get 4, and 4 is too small for our request, so we'll go back to 8, and 8 is therefore our final chunk size. So it's the idea here, we repeatedly halve our size, our block size, or divide it into 2 repeatedly until we can't do that anymore and maintain, until we can't do that anymore without being able to fulfill the request of, say, 7 kilobytes in this example. So here, just to reiterate, we keep on dividing in half until we get to 8, and we stop at 8 because if we did it one more time, we wouldn't be able to fulfill the 7 kilobyte request. So now what we do is we allocate this chunk as would become our allocated block, and then everything else would be in our free block. So this is called our buddy allocation approach. And this is the last component that we're looking at today. So once again, thank you very much. I hope you guys understand these different techniques. If not, feel free to ask any questions on the Moodle page.